So good morning. This is the last lecture on computer control. And today we are going to speak about dynamic programming. This lecture, I won't make any questions about this lecture on the next second test. So if you come to the second test repetition on January, or to the exam on January, you can have questions about this issue, but not the second test that we are going to do on Friday. So that you can have time to study, or if you just end the course next Friday, it's not mandatory, but this is an important topic. Okay? So what is the point here? The point here is that you want to optimize a function, but the function depends on the vector, which is the state of a dynamic system. So it's a dynamic optimization problem. Okay? That's why it's called dynamic programming. The roots are very, very old, 3 centuries old. Okay? But these ideas were somewhat lost, and it was more or less in about 70 years ago, in the middle of the 20th century, that Bellman reformulated them and rediscovered them, together with some other researchers in France and also the United States. And he coined the expression that we use, dynamic programming. So the idea is to use this optimum principle. Suppose that you live at you live at some house in point A, and Instituto Superior Técnico is at point B. Okay, and by some mean you find the optimal path between your home A and Instituto Superior Técnico B. And so you find this optimal path. Okay, so it's, for instance, the path that consumes less energy if you come using a bike that is an electrical bike. So this black line indicates the path that corresponds to the smallest use of energy, to the smallest energy spent in going from your home at point A to Instituto Superior Técnico at point B. Now, suppose that by some means you came to point C, which is over the optimal path. And so you ask, what is now the optimal path to go to Instituto Superior Técnico? You can do a formal proof, but it's quite intuitive that it would be the same that you would follow if you started from A. So if you start at any intermediate point in the optimal path, the remaining optimal path is the same that you would take if you were starting from the beginning at A. Okay, this is deceptively simple. It's Bellman's optimal principle, and let's see how we can use it. This is the idea. The idea is to characterize each state by a value. Okay, the value is the value of the objective function when you follow the optimal path till the end. Okay, so if you are at some state and you want to operate your system up to the last moment in which you are defining your operation, the operation of the system, you can apply a different sequence of control actions. Now, think of the one that optimizes your objective function. Okay, that's the value of the state, or the optimal value, better to say. Okay, the optimal cost to go. okay? So you have a cost from going to some state to the end, and if you follow the optimal sequence of controls, you have the optimal cost to go, and this is the value of the state. Now, you imagine that you consider all possible states, and that you assign the value to each of the states. Then you can also compute, as we are going to see, the optimal decision to take when you are at this state. Okay? So it's the idea is that you just select the sequence of controls that minimize or optimize the objective function starting from the state, which is the value. Now, what can you do? You start, imagine that you do a sequence of operations that consists of the following. First, you start at the ending point, so no decision to take. That's a final, that's the final condition. So if you start at the end point, it's very easy to find what is the cost. It's probably some terminal cost or even zero, depending on how you formulate the problem. And in a moment, I'm going to write some equations. And the decision is do nothing. Now, suppose that you are supposed to achieve this terminal point at some time, let's call it capital N. Now, go backwards 1 point. So go to point N minus 1. So you have just one decision to go to the terminal point. Optimize that decision for all the possible states. And you get the value at each state at time N minus 1, and then go backwards. Okay. So when you end, you have a table that assigns to each state the value and the correct decision, the optimal decision. Correct in the sense that it is the optimal one. Okay? Now, you can apply this strategy if you have a finite number of states. We will start by doing an example like that. If you have many states, or an infinite number of states, in the case where your state is continuous variable, such as a position and a velocity, then you will have a problem applying this method. Okay? But we are going to solve at least one problem with this method, and then I will tell you why am I speaking about this approach to optimal control. So let's make things more concrete. Suppose that you have a network and you want to go from A to B, and you can only jump according to these passes between these nodes. Okay, so you have nodes A, C, D, E, F, etc., and you have these passes. And when you travel along, say, from A to C, you spend 4 units of energy, and you want to find the least possible energy. So you want to travel from A to B by some pass, say, for instance, A to C, C to E, E to H, H to B. That corresponds to a cost which is 4 plus 8 plus 1 plus 2, which is 15. Okay, 8 plus 2, 10, 1 plus 4, 5, 8, 15. Okay, but if you travel from A to D to G to Y to B, then you spend 13 plus 7, 20 plus 3, 23. So it's better to go the other way, but you don't want to decide between just 2 passes. You want to consider all possible passes. Now, you could do the computation for all the possible passes, but instead we are going to use this algorithm of dynamic programming. And in this way, we are spared to compare a number of costs. Okay? So the total amount of costs that you have to compute is smaller when you use dynamic programming than when you use just brute force and consider all the possible combinations. Now, this is a very simple graph. You can do it easily. But if you have a larger graph, then you can fall into trouble. Okay? So let's apply dynamic programming to this to find the optimal path between A and B. And remember, what is the idea? The idea is that you take some state, for instance, F or any other state, and you want to label F with two numbers or two things. One is the optimal cost from going from F to B, and the other is the correct decision that you should take when you come at F. Okay, so let me. I have this class, this lecture prepared to discuss it in the class, in the blackboard. We don't have a blackboard, but we have a whiteboard. So let me change my screen. Okay, just to remember, because you can't see it, let me plot here the network, and this is A, this is C, E, H, B, this is I, this is F, this is G, and this is D. And then from A to C, the cost is 4, 8, 1, 2, 3, here 8, 2, 8, 2, 7, 11, 5, 1, 2, and that's it. Okay. So the idea is that you start at the end to do this, to apply this technique. You start at the end at point B. Okay, if you are at point B, you go to point B. So if you are at state H, well, you only have one decision. Go to B, and the cost is 2. So the value of H is 2. Okay? If you don't understand something, please interrupt me. Now, if you are at I, again, you can go to B, and the value of I is the value of the branch between I and B, which is 3. Now, let's go back again one. If you are at E, you can only go to H. And then, once you are at H, you apply Bellman's principle that states if you are at some state, the optimal cost to go, the optimal decision is to take the optimal path independently how you arrived at H. So no matter how you arrived at H, independent that before was optimal or not, you should go to B. And so your cost, which is your cost at E, which is the value of E because you don't have any other option, is the cost of going from E to H, which is 1, plus the value of I, plus the value of I, which is the value of I is 2. We have computed it there. So the value of E is 3. Now, if you are at F, things start being more interesting because you can go either to H or you can go to E, I. If you go to H, then you spend 8 going to H, and then the value of H is what? Is 2. Look at the first row. So this is 10. But if you go to I, you spend 2. That's the cost between F and I. And then you add the value of I, which is 3, second row here in the whiteboard. So it's 5. So the optimal decision is going to I, and the value is 5. So the value of F is the optimal cost to go to B. It's 5, and the optimal decision is F. Now, if you are at G, you should go to I. So your cost now is 7, and then the value of I, and the value of I is 3. Now go back again. If you are at C, you can go to E on the top, or you can go to F. So if you go to E, you spend 8 plus the value of E, which is 3. And this would imply cost of 11. If you go to F, the cost is 1 plus the value of S, which is 5. So if you take that option, it costs you 6. So you select the best one. So you should go to F, and the value is 6. If you are at D, you can go to F or to G. At this point, you now understand what is the procedure, but let's take it to the end. Don't go asleep, okay, please. So if you go to F, it's 5 plus the value of F, and the value of F is 5. So that's 10. If you go to G, that's 11 plus the value of G, which is 10. It's written here. So it's 21. Now, the best choice is to go to F. Fine. Now, finally, if you are at A, you can go to C, or you can go to D. If you go to C, it's 4 plus the value of C. Where is the value of C? The value of C is 6. Is 6. So it's 10, the sum. And if you go to D, it's 2 plus the value of D, which is 10. That gives me 14. So the value of A is 10, and the correct decision is go to C. So if you start now at A, where should you go? You should go to C. And from C, you should go to F. Okay, from A, you should go to C. From C, you should go to F. And then at F, you should go where? You should go to I. And from I to B. Okay, so this is the optimal path. So what have we done? What we have done is we started at the end, at point B, and then we came backwards in time. I mean, going from one level of nodes to another level, I call it a pseudo time, and or decision level if you want. And we go backwards. Okay, so in dynamic optimization problems, you usually go backwards. You start at the end and you go on considering more and more decisions. So you go backwards and you do a table in which you compute the value of the different nodes, and the value is the optimal cost to go to the final point. And also you take care, you take note of the optimal decision, and then you progress, okay, from level -1, -2, -3, and so on. Okay, any question about this? Okay, so let's go back to the slides. So I think that I will learn how to use this proficiently when I end the course. Okay, so this is a system, a situation in which we have a finite state. So we have a finite number of states. Now we can consider a situation in which we have an infinite dimensional state. That's a situation when you have, for instance, this nonlinear state model, okay, in which f is a function that maps the state at time k. There is curl bracket missing here. So it maps f(x) of k plus 1 is a function of x of k and of the decision that you take at time k. And you start with some initial condition. Now, suppose that you operate this from for a number of steps, okay, from k equal to 0 up to k equal to n minus 1. So that's n steps because you started at k equal to 0. Okay? For instance, you are operating, you are selecting the heating of your room for a period of, say, 24 hours. And you consider the energy spent every hour. Okay, so you have a sampling interval of 1 hour, okay, and you somehow you write the equations for the balance of energy and so on. So you build a model of the energy spent in each of the divisions of your home. So the state is the temperature, say, at each of the divisions, and you compute the energy L spent every hour. That's the instantaneous cost L at each time, and you want to minimize the cost of energy. Okay, So in some problems, you also add a terminal cost. So when you come at the end, you have something that depends also on the state. This can be zero, or this may not be zero. So it's an extra degree of freedom. Okay? So what you want to do in the example of optimizing the energy spent in your home, you want to find the optimal profile of heating, that's you, during the day. So how do you adjust your heater every hour such that you minimize this cost that depends on the energy spent, and also probably some term in which you force the temperature to be close to some set point. Okay, so you have a balance between spending energy, okay, that's related to you, and having the temperature close to some set point. That's an example. Well, probably no one pays you to do this for your own home, but if you have a supermarket or a shopping center, a big mall, you can apply these techniques, and you can have a model for the shopping center, for the consumption of energy in the shopping center, and you want to optimize the air conditioned and heating, and also light, the energy that you spend on light, and these are elements of a vector of use. Okay, and this L is the energy spent every hour or every 15 minutes, and you want to minimize it for a period of 1 day. So if you consider the sampling time to be 1 hour, capital N will be 24, corresponding to the period of 1 day. Okay, so we have the dynamics that tells you how the state evolves. And this is not new because we have spoken about the state model with some initial condition. And we have a cost. We have an objective function, okay, which is a function of the sequence of u between 0 and n minus 1. So I wrote this u, I wrote this function as in this way, u from 0 to n minus 1. So vertical slash, and then between brackets 0, the initial time and the final discrete time. Okay, so this actually means u0, u1, u2 up to un minus 1. And you want to minimize this sequence, and x and u are related by the state model. Okay, so we want to find a sequence of control values that optimizes this objective function. And we are going to write an equation in the general case that allows you, that gives a condition for u to be optimal. So according to dynamic programming, what you do is to define a value function. Okay, if you are at time k, the value function of a state at time k is it's the optimal cost when you operate the system from time k up to the end. So the value of x at time k, okay, is the minimum of, with respect to the sequence, the remaining sequence of points between k and n minus 1, because previous ones, they have already been decided, okay? And all the information about them is on the state. You reach that state, and then you have the cost between k and n minus 1. If you look at the cost is defined for k equal to 0 up to n minus 1. Here, my index goes from k up to n minus 1. Okay. And this is the value. This is the value. Now, how can I compute the value? You do it by progressing backwards, as we did in the network example. So what you do is imagine that this horizontal axis is discrete time between 0 and n. Actually, you are operating up to n minus 1. And now you want to compute the optimal cost to go to the final time at time k plus 1. And we are going to relate this with the optimal cost to go from any state at time k. Okay? So you are progressing backwards, and you given the value of a state, of a general state x. So for any point in this axis of the state at time k plus 1, assume that you know the value. Now, how can I compute the value at time k? So the previous instant. Okay, so I want to compute the value of any state x at time k from the value of any state x at time k plus 1. Okay, and we are going backwards. So the direction of the progression of the optimization is to the left. Okay, and you can do this because you start at the end, and at the end, the final value is, say, 0, because you don't have any terms, or if it is not 0, it's this terminal cost here. But you don't have any decisions, then you consider n minus 1 and then n minus 2 and so on, and you go on back computing this backwards. Okay, so what is the relation of these two quantities? It's very simple. It's very simple. It's written here. Okay, it's so simple that I was trying to find another slide, but it's here. Okay, so you can relate the states, the value at time k plus 1 and the value at time k by, there should be here one line in which I isolate, remember the definition. So I write, I isolate the time, the term of this summation at time k, and then I have a summation from time k plus 1. If I have the summation at time k plus 1 plus this psi, and I take the minimum, that's v of x of k plus 1 plus one term, which is the L that appears here. Okay, so this equation, which is the so-called Hamilton-Jacobi-Bellman equation in discrete time, it's nothing more than this difference equation. Okay, in which you have the u at time k. Okay, you have the u at time k, and this is the value of the state at time k plus 1, and this is the value of the state of a general state x at time k. Okay, so you optimize, you isolate just one time, and you optimize, and you use the Bellman's principle to remind you that actually this is the optimal cost to go, because you are taking, when you do this minimization, you are, it does not matter how you reached the state at time k plus 1. Okay, so you have to solve this equation. Now, this equation is not so, looks not much complicated, but actually in practice there are only a few situations in which you can solve it. Okay, one of the situations is the linear quadratic problem. So let's apply these ideas for the situation in which f is a linear function of x and u, and L is a quadratic function of x and u. Okay, so suppose that your dynamics is x of k plus 1 equals to phi x of k plus gamma u of k. So the linear dynamics, sometimes you call this A and this B. Okay, so I'm using Greek letters here. And the cost is a quadratic cost. So we have a quadratic cost function in x and a quadratic cost function in u at time k. And we also have a panelization of the last state, okay, at time n. Now, if you are at time n, the value is just this term here, because you only consider the very last term. So v of xn is nothing more than x transposed n q0 xn. So this terminal term. Now, what is the right Hamilton-Jacobi-Bellman equation, HAB equation? It's v of x of the state, the value of the state at time k, is the minimization with respect to u of what? L of x of k u of k. Okay, I'm omitting the k here. Plus the value at time k plus 1. Okay, the value. But the state at time k plus 1 is phi x of k plus gamma u of k. Okay, because of the model. So this is the equation that we want to find with respect to v. What can we do? What can we do? We assume that v is a quadratic function of x. Okay, this has to be proven. We can prove it a priori, a posteriori, that is to say. We assume this from the beginning. From the beginning means a priori. And we try to find a solution of this form for the HAB equation here that I wrote in the first line. And if we find a solution, then okay, we have concluded that v can be written in this way. Okay, so what do we do? On the left, I find the value as x transpose p of k. X actually is x of k. Okay. Now we have x of k qx. Okay. And that's a terminal condition. This is the terminal condition. This is actually x is here at n, so it's not affected by u. And then we have this term here is u transposed ru. Actually, I did some simplifications. And v of phi x plus gamma u, I put it here, and then I've simplified things, and I was lazy when I wrote this slide, so I wrote already a simplification. Okay, you see that you have here u transposed ru, and then you have u transposed gamma transposed pk plus 1 gamma u, which corresponds to this term here, plus the other terms. Okay, so this is nothing more than writing v of phi x of k plus gamma uk, assuming that v has this form. So replacing here x by phi x plus gamma u. Okay, so I have to minimize this with respect to u, but this is a quadratic form in u. You have here u transposed u. This is a matrix that does not depend on u. This is a linear term on u, and this is a term that is independent of u. Okay, so what can we do? We can compute the gradient, or we can find the value of u that minimizes this term here in this way. Suppose that you have some generic quadratic form u minus u star. U star is a constant transposed some matrix M generic m minus u star. Okay, And the minimum is clearly U equal to U star. So see how this develops when you expand this product for some matrix. So you do all the multiplications and you get what is here. So it's U transpose MU minus 2 U transpose U star transposed MU plus U star transposed MU star. Now compare this expression with that expression there. Okay, you have the U transposed MU. Then you have here, you have 2 X transposed phi. So M is this stuff. Okay, and I wrote it here. And then minus 2 U transposed M is 2 X transposed phi transposed P of K plus 1 gamma U. Okay, gamma, because I just stop here. Okay, so this part here is that part here up to the U. Now the U star is M inverse, is minus M inverse times this stuff. Okay, so you end up with the conclusion that U star is some vector that you compute in this way times X. Okay, and furthermore, if you compute now, you have, if you eliminate U, replace it by the optimal value given by fx with f given by this expression here. So you get rid of the minimization term because U star is the one that minimizes with respect to U all this stuff. So you will have everything with X transposed on the left and X on the right. So you have X transposed PK X equals to X transposed QX plus, and then you remember that U star is f of kx. So you will have here X transposed, F transposed, okay? And on the right you have you will have fx and so on. So for these quadratic forms to be the same, the matrices of the quadratic forms must be equal. So P of x must be Q plus this quadratic form. Okay, this takes some lines of manipulations, but in the end you get this equation for P. That's the so-called Riccati equation. So what is the solution of this problem? The solution of this problem is given by this. So solve P that depends on K, the solution of the linear quadratic problem. So we have linear dynamics and quadratic cost. You should find a matrix P that depends on K and satisfies this equation. You see that PK is given in terms of PK plus 1. So you end up with a terminal condition, and then you go backwards. And the terminal condition is obtained from the fact that the terminal cost is X transposed Q0X. So the final P of n is actual to Q0. Okay, so remember that V is X transposed P of n X. So P of n must be Q0. So you start with that terminal condition, and then you go iterating backwards from K plus 1 computing PK. And once you have P for all K, for all the times K from the end to the beginning, you can compute the gain F from the end to the beginning. Now, what happens is that if the horizon, this horizon n is very large, so if it is infinite, okay, you can show that provided that f and gamma, remember the controllability conditions that we spoke about when we were speaking about the existence of the pole place, of the solution for the pole place problem. If phi and gamma is controllable, then when n goes to infinity, then what happens is that pk approaches a constant. So this becomes an algebraic equation. So put here some p that does not depend on k, and here put here the same p that does not depend on k plus 1. Okay, and so you have an algebraic equation that you can solve using numerical methods. And also the gain becomes constant because the gain depends on p. If p is constant, f is constant. And furthermore, this is a stabilizing gain. So this is the controller gain that you get when you use the DLQR routine in MATLAB. Okay, it appears in this way. So the computations seem a little bit complicated. They are not. I mean, you probably should be able to fill the gaps doing the algebra that is missing in this slide. But the final result is conceptually very simple. So to compute the optimal gain, you solve this equation. Okay, you don't know how to solve it by hand. If it is a scalar problem, if the state is a scalar, then this can be reduced to an algebraic second-order equation. And then you compute the gain using this expression obtained that involves the solution of the Riccati equation. When the problem is not a scalar one, so p is not a scalar, you have to resort to numerical methods to solve this equation. But then that's why we use DLQR that solves this so-called infinite horizon problem. Okay, so this is one use of dynamic programming, is to solve the linear quadratic problem. Okay? It's not a small use. Now, perhaps one thing which is much more interesting, but unfortunately we are not able to speak about it, is to use these ideas to develop adaptive controllers, using a technique related to artificial intelligence, that's reinforcement learning. What is reinforcement learning? Suppose that you want to train some device that is able to change his behavior depending on stimulus. The device can be, say, a dog. Imagine that you have a dog and you want to train it. Okay? Now, suppose that you want to train the dog to sit down, okay, when you order him to sit. And so what do? You say sit and force the dog to sit down. When he sits, you give him a reward. You give him, say, a piece of meat or some cake or something that he likes. And when he does not sit, you speak hungry to him. Okay, no, that's not correct. Okay. And so you show himself that you are displeased. So you are giving the dog a reward when he develops the action that you want to be taken. Okay? So the dog will learn by maximizing his reward. Okay? This is a very old idea that comes from the 19th century, from a Russian called Pavlov. He did a number of controversial experiments, but the idea comes from that. And it's also in contrast with learning that you have studied probably in courses of artificial intelligence, which is usually supervised learning. That is to say, you have a master that tells you whether you are doing correctly or incorrectly. Okay? Instead, here you give a reward, and in reinforcement learning, which is unsupervised learning, you give a reward. You don't say it's correct or incorrect. You give a reward. Okay, and you can use these ideas for control by defining a reward which is associated to the cost. Now, usually you want to maximize a reward. Here we want to minimize the cost. But it's not a problem. I mean, if you multiply the cost by -1, then you want to maximize minus the same metric of the cost. Okay, so minus v can be seen as a reward, and the result is completely the same. So sometimes I call reward to the cost. Okay, in this case, I want to minimize it. And well, the exact solution verifies this Hamilton-Jacobi-Bellman equation. But we have seen that the Hamilton-Jacobi-Bellman equation has a number of problems. So a number of guys did two things. One thing is to find versions of this equation which are approximations, and they are simpler to solve. They only are concerned with the states close to the optimal trajectory. Okay? And the other thing is to approximate V as a combination of basis functions or neural networks. So you approximate your value using what we can call in general an approximator. Okay, can be, for instance, a linear combination of quadratic functions that works exactly as we have seen for the linear quadratic problem, because the cost function is a quadratic function. Okay, that's nice. If the dynamics is not linear, then it's just an approximation. Okay? Or you can use other types of basis functions. You can use linear combination of other basis functions, or you can use neural networks. Okay, and then you adjust the coefficients of the. You know that you know that when you progress in time, the reward in different times is related by things that are approximations of this Hamilton-Jacobi-Bellman equation. Okay, that's the idea. And then you can build algorithms to propagate V, or if you use neural networks, that's the quality of your decisions, which is a function of X and U. That's the same thing. That's pretty much the same, satisfies pretty much the same thing, but now it's a function of X and U. I'm not giving you the details. That's the quality function, and that's Q learning, maximizing the Q function. It's the Q learning. So the Q function is something that gives you the reward as a function of state and the control U. And you approximate the Q function using, for instance, a neural network or a linear combination of convex functions. And from V, you can, by doing this minimization, this minimization. You can find finding the argument U that minimizes this quantity. You can find the optimal cost in this way. Okay, this is the approximate dynamic programming, and it's a quite powerful method to design adaptive controllers for nonlinear systems, which are related directly to optimal control, because we are optimizing a reward. Okay? So perhaps this would be the interesting thing, but we don't have time to study it. So I just call your attention to the problem. If someone is interested, I can give you a tutorial paper which is adequate for you to read. What should you know concerning computer control, the computer control course, and the exam? You should be able to understand this idea of defining the value function as the minimum function to go from any state x from k up to the final term, that it is related by this HJB equation, okay, and then the application to the linear quadratic problem. I can do problems about this, and of course there are some examples like this one with the networks. So this concludes the course on computer control. You have any question?